My name is Matt Padera, and for Lab 9, I created a self-calibrating automatic ball launcher. And now for a quick description of the Arduino code, the back-end logic that programs the device. This is going to be a very quick run-through. If I had more video time allowance, I would go into a much more detailed description. But basically, the setup, we assign pin modes and calculate a launch velocity that is based on the calibration airtime for a vertical launch that changes between different rubber band applications. The first step is to calculate the launch velocity, which is based on the calibration airtime as previously discussed. This is just a kinematic equation for a vertical launch. To detect dx, so this is detecting the horizontal distance, linear distance away from the ultrasonic sensor, and basically reports how far away the cup is, and then this will be used for kinematic equations later on. From there, we jump to our calculation of the launch angle, which is just a kinematic equation that I derived as theta as a function of dx. We calculate the launch angle and then go to adjusting the angle, adjusting the angle servo with a T-control that is mapped with theta of 0 to 90 degrees and then pulse widths of 1525 to 2400 microseconds. After that, we go to firing this projectile, which is very similar to adjusting the angle servo. We just adjust it from 120 degrees to 0 degrees, and this is the firing servo. And then finally, we apply all the back-end functions, taking an average of the dx, 100 samples in 1 second, and then applying that to adjusting the angle for launch. And then the loop function is just detecting whether the button is pressed for calculating and positioning versus firing. To get into the front-end code that powers the user interface, we define the serial and processing, import the cup image, and then have some global variables at the top. We'd clear the Arduino port, size the window, and then load in the image. In the draw function on startup, we have a visual of the launcher with a white circle and a line representing the ground. While the Arduino port's available, we read the string coming in from the serial monitor and trim off any white space, and we split the values into an array. If the array length is 3, that means we have the VI, DX, and theta values, and then we map a cup X coordinate based on the DX value with a range of 0 to a table length of about 1.5 meters, and then from 100 to 1100 pixels, and then print calculations. If the array length is 1, that means we're currently launching, and then we go to the print ball function. In print calculations, we're printing the cup image and then displaying our calculations. If theta is -1, that means it's too far away. If theta is 90, we're calibrating the launcher, and then otherwise we're calibrating as normal. In print ball, we're calculating the horizontal and vertical components of the velocity. We're calculating the maximum height for this specific application, and then we're going through a for loop of 500 iterations with the ball X and ball Y values in meters as a function of time, with the T final value calculated here, and then we map the ball X and ball Y into pixels and then draw balls as it's launching to form a parabola. If T becomes greater than the T final value, we break the loop, and therefore it never actually reaches the 500 iterations. And then from there, we're basically printing a graph corresponding to the maximum ball height in meters, and then 4 increments below that. And now to demonstrate the processing, I'll place my hand in front of the sensor to indicate calibrating distance. And then to actually detect the DX, places the cup accordingly and prints the values. To fire, we can see the graph produced, and then I'll demonstrate where the DX is too far.